Hi everyone, Kurt with HypnoDyne again. In the last episode of Scoring Sleep with ZMax, we took a look at the spectrogram, and I taught you how to find the most common spectrogram features, including spindles, alpha waves, eye movements, and more. Today I would like to open a couple of recordings to see how these features actually vary between people. So that if you get ZMax and you look at your own sleep, you're easily able to, have that kind of awareness of how these things change among people, so that you can look at your sleep and say, all right, that's not a problem. I can see how this is working, right? So I will give you a few seconds to take a look at this spectrogram and find where the sleep spindles might be occurring and what the main sleep cycles are. You may want to pause this video and figure it out, and then we'll see if you got the right answer. Okay, so the solution is the first sleep cycle starts here and ends here, with the spindles being this horizontal ridge. Second sleep cycle starts here and ends here. It's another sleep spindle ridge indicating slow wave sleep. Third sleep cycle from here to here. Fourth sleep cycle from here to here. Fifth from here to here. And you should know that towards the end of the night your sleep pressure is decreasing, and so you no longer see such huge sleep cycles. Your sleep stage tends to oscillate back and forth much faster. So for example, we have a very short period of slow wave sleep from here to here, and another one from here to here. Technically, I don't know if you can call it a cycle. It's not really a cycle. It's the end of the night, let's call it. One thing that's interesting on this spectrogram is that this person actually has a type of alpha that is not as is commonly taught. If you open any web page that tells you about alpha waves, they will tell you alpha occurs at 10 Hertz and spindles occur at 12 Hertz. That's not always the case. For example, here we have alpha. See how tall it is compared to the sleep spindles ridge? Not only is it tall, so it's probably going from 8 Hertz to 12 Hertz, but it's overlapping the spindle frequency. Now, nearly all of the sleep scoring algorithms, and this is including stuff that's published on PubMed about people telling you different types of algorithms to score sleep. They always call these sleep spindles, they call it the sigma band. It's just another way of calling it. But they all seem absolutely diluted into band pass filtering the signal. And what that means is just, imagine that you didn't have this portion on the top. I don't know how I can show it to you on the screen. Let me open a window, okay? Let me use the window to chop off the spectrogram. Imagine that you didn't see anything below that. And then I'm also gonna cut off the top so you can see. Oops, better make this thinner. And I can't. Okay, let me resize the window. I want to show you what these folks are doing. And we're talking like sleep researchers, right? And then they would chop off this other segment here. That's what happens if you filter the signal. It's called filtering. You just chop off everything except a particular frequency. Chop here and you chop here. And by doing this, most people seem convinced that you can actually get a measure of the spindle activity. Now, if you did this in this signal, because the alpha frequency is overlapping with spindles, this part right here would show as having high sigma activity, which is wrong, because they didn't look at the spectrogram. Now, these are sleep researchers that are publishing scientific papers on automatic sleep scoring. So I only leave you to imagine the consumer devices that don't give you the raw data and that are intended for consumers that don't know about sleep structure. Imagine the lack of accuracy that goes on with those things. But I want you to know better. So this is alpha, and you can see that easily because there's a little gap right before the spindles, and because it does have a lower frequency component, but it's still overlapping with spindles. So what you see immediately from this person, the first thing to notice would be, hey, this person, at least if you're somebody trying to develop algorithm for scoring sleep, for example, would say this guy has, or gal, I don't know who exactly this is, anonymous participant from a sleep study. But this person has alpha activity that overlaps spindle activity. This is what's making automatic analysis of sleep so difficult compared to visual scoring. Now, visually, if you're a human scorer, you just look at the spectrogram and you realize this is alpha. Then you can move into the signal and validate it as well. You can see that this frequency activity, whatever it is, it basically begins right after an arousal. This is, of course, the accelerometric data. So this is a body movement. And right coming out of that body movement, that kind of zigzag wave already is beginning. And this is very noisy. So if I were to just look at this, I'd have no idea what's going on. But looking at the spectrogram and the signal, you get an idea. But the point is, you've got this zigzag that goes on and on and on and on. You know, sleep spindles are not like that. And I'm just talking if you were confused, right, and you didn't have this. These sleep spindles, they come and go. Normally they last a second, and not more. So you can see a strong sleep spindle here. You can see another one right here. And you can see one here, very strong, very localized, another one here, another one here. Alpha is continuous. It can go on for several seconds. So this kind of zigzag activity, and you know, don't panic if you can't see it, because this signal is actually very confused here. This is still during a wake period. But the alpha keeps on and on. Look at this high frequency zigzag activity. It just goes on and on and on. Something that lasts this long is alpha for sure. And you don't need to even look at this. Just completely ignore it. In fact, it's very messy, it's very confusing. Just look at this. You see a small gap. There's always a small gap in between alpha and the first sleep cycle. And that tells you, that's alpha. Okay? Now, sorry if I spent so much time on this, but this really, you know, it was a big discovery for me, because nobody seems to be talking about it, and people who write the algorithms routinely ignore the existence of phenotypes and the fact that alpha can overlap spindles, and it just, I don't know, it's just a very confusing thing. But when you know that it's like that, then fine, you don't have a problem. Now, knowing that this is what alpha looks like in this person, you can move throughout the signal and see where else does this kind of activity occur. And if you catch that right, you would find other periods of wake. For example, here's a period of wake. And in fact, you see that there's this zigzag activity, and it's very long. Like here, it's from here to here uninterrupted. So that's all alpha waves. And here's another bit of that. Just coming out of an arousal, that's another telltale sign. Because normally, if you have an arousal, it takes usually some time before your brain begins to produce spindles again. Whereas if you just woke up and you're producing alpha activity, it's going to start right away. And then again, the fact that it's continuous and not occurring in short bursts also gives that away. Okay, so this is a person that has this kind of alpha activity, and it occurs in several places because, you know, they're waking up throughout the night. So that's interesting. Another thing that I want to point out to you, though you don't really need it for sleep scoring, but as a curiosity, this thing right here is beta activity. In my sleep, beta activity occurs during REM, but for this patient, it occurs during wake. I don't know exactly why. I don't think anybody knows exactly why. Sleep is still, you know, most of sleep is still a mystery, but it's just a curiosity. You don't need this for scoring sleep. Okay, so this is one person that has this slightly different phenotype. Let's open my recording, because I have yet another phenotype. Mine is actually really puzzling, and you know, as I was developing ZMax, initially all I could see was my signal. And it's actually so regular, I don't know, I'm like a robot. And I thought, well, sleep scoring, automatic sleep scoring is going to be super easy. And then when I started looking at other people's recordings, I realized, oh God, that it's actually super, super hard. But because you see, in my case, well, okay, so I give you a few seconds to find find two things. Find sleep spindles and alpha activity. You can pause it now. Okay, so alpha from here to here, and sleep spindles starting right about here until here. That's the first sleep cycle, and so on. The reason my sleep is so easy to score, like you could do it really naively, is first of all, there's no overlap between the alpha frequency and the spindle frequency. I'm going to do this stupid thing again and chop it off so you can see what I mean. Like if I occlude all of that part, okay, now I can only see spindles. I can't see the initial alpha. And if I were to chop it off after that, see? In my case, if you naively filtered and you knew the exact frequency of sleep spindles, you could determine the slow wave sleep cycles in a very naive manner. Now, another curiosity here, I've got two alphas. You see that there's some kind of a gap in between? Now, I suppose, but I'm not sure of this, that everybody has two alphas, but sometimes they're so close that you actually see them as only one. Or perhaps one is too faint and you can't see it and you only see one. And perhaps when your alpha is really strong, then you can actually see that there's two. Interesting stuff. You can see, as I was saying before, that there's a gap between when alpha ends and when sleep spindles begin. So that's the gap. You're starting to notice some regularities. Going back to the sleep spindles, you see the first cycle from here to here, second cycle from, let's say, here to here, third cycle from here to here. And you remember that I was showing you beta waves in the other subject. But in my case, beta waves actually occur during REM sleep. And yeah, I haven't seen so strong beta waves in other people's recordings. Another curiosity, right? So here you got these beta waves. And since you notice that these gaps in the sleep spindles, for sure coinciding with REM sleep, have so much beta, and you might be wondering, well, what on earth is going on here? Because I see some sleep spindles, well, they're faint, but there's some, and also beta. So what is this? Is this a mix? And it is a mix. It's, you know, I guess the brain kind of going back and forth between slow wave sleep and REM sleep. So in a spectrogram, these values get averaged, and you can sometimes see that the frequency activity superimposed. So that's an interesting thing to notice, just to look at some variety in these signals. I want to show you another person that has even more extreme double alpha activity in the beginning. Let's see if I can find her recording. It's opening the files. Not sure what happened to my window frame right there, but okay. So in her case, look at this. This is all alpha activity. This is the famous gap between alpha and the sleep spindles. And you may see that the alpha waves are actually disappearing. And first thing I would want to check is why. So I would move on here. I see massive eye movements. So she was probably reading something before falling asleep. And these eye movements have actually, they're so strong that they have created this whole flooding of the spectral intensity, which then gets wiped out by the X-ray. So I don't mean to get into too much detail and make this painful, but I'm just following my own chain of thought as I look at this recording. But yeah, so just like in the other recordings, these are the sleep spindles, and the activity ends right there. It's the first cycle. And we have a second cycle from here to here, another cycle from here to here, and so on and so forth. And I actually lied. I said that I didn't know any other person who had beta activity as strong as mine. Actually, she does. This is also beta. I wouldn't really look at it for scoring though, because there are times in which, I mean, you could vaguely associate beta activity with REM sleep, especially when you have these holes and there are no spindles. But the thing is, sometimes beta activity starts before the spindles end. So it's not really a one-to-one thing that you can rely on. So it's pretty though. Anyway, another thing I noticed looking at this is this really bright dot. I would bet that she woke up right here and that's alpha activity. In fact, let's see, I move on it. And there you go, there's an arousal. These slow eye movements normally occur as you're falling back asleep. And there's a continuous zigzag activity. So that's actually alpha, and she's awake right here. Now, yeah, I want to point out, see, it's just a dot. It's not a double peak for alpha. Whereas here, it's double. So one thing that I realized working on so much sleep data is that the alpha waves that you emit as you're falling asleep prior to the sleep onset don't really necessarily need to be identical to the alphas that you emit when you have an arousal throughout sleep. That's curious. I don't think anybody knows why, but you know, if you postulate that there's some kind of different reason for the two alpha bands, perhaps that reason is just not there in this case during an arousal. All right, but you know, I think the basic point is that this is alpha. You would know A because it occurs right at the beginning, B because there's a double ridge, C because there's a gap in between that and a higher frequency activity of the spindles. And yeah, that's basically all the reasons. So again, first sleep cycle, second sleep cycle here to here, third from here to here, fourth from here to here, and here it starts to get really messy, and I think it's because here the sleep pressure has decreased a lot, so yeah, it's probably very, very weak N2 sleep. We do see some sleep spindles, but not frequently, so that's why the spectrogram shows very weak ridge at the spindle frequency. All right, but all you're supposed to get out of this is just to have another example of a phenotype, so that when you open your own sleep, whether you have one alpha ridge or whether you have two or none, you're still able to say, okay, this is when I fell asleep, and before that, that's all wake, and these are my sleep cycles, 1, 2, 3, 4, and 5 by here. By the time I got here, my sleep was already not very heavy or deep, which is a good thing. It means that this sleep was relatively heavy and stable, so that you relieve all your sleep pressure within the first, you know, however long this is. We have beautiful, beautiful spectrogram quality here. Let's look at the X-ray. All right. So if you want to try your luck finding the sleep spindles, I'll give you a few seconds. You can pause the video. All right, the solution is first sleep cycle starts here, ends here. Second sleep cycle starts here, ends here. Although there's a little tiny dot of slow wave sleep right here. So third sleep cycle here to here. Fourth here to here. And I guess you can say fifth, even though she's going in and out. I would point out on this recording that this kind of like a cloud right here, yeah, so that's probably alpha. And I guess what that's telling you is that in her case, the alpha frequency is not very constant. It's all over the place. So what happens is that all of the light intensity, if you look at the spectrogram as an image, right, all of the intensity that should have been focused on a narrow band so that it would make it nice and thin and regular and appear in bright yellow like the spindles, instead of that, because the alpha frequency is not constant, it just appears like a cloud, and it's quite dark. In fact, this is a very, very dirty recording. I don't know what she's doing here. Let me see. Well, the accelerometer is flat, which means she's not moving around. But these are very odd waves. They're also really strong. Really should zoom out a little bit. Anyway, I placed the beginning of the first sleep cycle right here, and I've done that purely based on the spectrogram. I'm curious to go and look at the data and see what the transition looked like. Well, we have some rolling eye movements. You see the signals continue to cross each other. There's slow rolling eye movements. That's N1 sleep. That's the transition between wake and sleep. So, looks like I got it right. And then I probably mentioned this dot right here, which is slow wave sleep. You can see a K complex. That's another one of the features of slow wave sleep other than the sleep spindles. Just looks like this. The wave goes down, up, and comes back. And it's another sleep spindle. And then there's a hole. So this should be a portion without spindles. Now, you can't really see that very much in this recording, but let me try here. Yeah. So you might be wondering, what about the strength of these sleep spindles? Because I can see here it's very strong. It's in yellow color. And as we proceed, it's getting fainter. Now what happened with this recording is, well, I can't be sure because it was a long time ago, but I think there's a lot of sweating going on here. The sweating makes the signal go out of range because this actually was acquired with an old version of the hardware. The new version of the hardware wouldn't do this, but the old version of the hardware, the signal was going out of range, and so it was missing some of the spindle activity because it was just the signal becomes invisible at that point. So you see it becoming fainter. There are recordings in which that's a little bit more dramatic, but it doesn't matter. It's still very strong. Totally allows you to determine that that's N2 sleep. That's a K complex. Goes down, up, comes back. It's a clear indication of N2 sleep. And so this should be the REM. Now, let's see if we can apply some of the teachings from the first lesson to find some eye movements just by looking at the spectrogram. As you remember, the eye movements are vertical bars that don't reach to the bottom of the spectrogram. So I'm looking for, well, how about here? This is a very messy recording due to brain activity mostly, but yeah, these are probably eye movements. And this is an interesting subject because she has these zigzag waves. They're everywhere, basically. And fortunately, her spindles are strong enough that you can still see where the spindles end and begin. But she does have a lot of background activity. And that's just her phenotype. I don't think anybody really knows what that means. But these are clear eye movements. So I've spotted these by looking at tiny yellow dots here at the top. So if you wanted to find where this person is dreaming, you would look at this hole from here to here. And then you would look at this hole from here to here. And then this hole from here to here. So just by moving randomly throughout the hole, you should be able to find eye movements. So these are eye movements, 1, 2, 3, 4. These anti-correlated bubbles where one signal is going one way and the other signal is going the other way, and then they flip over and get inverted. This too. And they're not as regular as in other recordings, and that depends a little bit on the direction that the person is looking. If they're just looking left to right, these things are going to be perfectly symmetrical. But it looks like she was looking sideways, so they're not perfectly symmetrical. This is kind of very symmetrical eye movement occurs when the person is looking just left and right, not at an angle. And this kind of stuff right here is when they're looking up and down. They're much harder to spot, so I don't really focus on these. They also don't frequently occur. You mostly see left-right eye movements during sleep. Okay. Well, I guess this is getting long. I didn't mean to make it so intense, but I just wanted to look at some of the sleep phenotypes with you so that when you try ZMax and you see your own spectrogram, you can have some points of reference to determine which one you look like. Are you the one without alpha activity or with the alpha, kind of like a cloud right here? Or do you have two alphas? And you'll be able to find these holes in the spindle frequency to look for your eye movements and figure out when your REM sleep occurred. And you'll also be able to look at the end of the night. Like in this case, this person just woke up and that was it. They just took off the ZMax. You don't see the same pattern as with other recordings. You know, when I pointed out that the sleep pressure had decreased, and so there's very confused activity where the brain is sort of switching back and forth between slow wave sleep and REM and slow wave sleep. And here it's not occurring. She just woke up in the middle of REM sleep and she took it off. I guess she couldn't take it anymore. A lot of spikes. She's figuring out. I guess she's just figuring out how to take it off, and she's moving around a lot. Okay. It's a problematic recording for automatic scoring because she has activity in the spindle range even when spindles are not present. It's strange. Like even if you look at the signal, it's strange. You click on some epochs and you can see a lot of miscellaneous activity that is not there in most people. So I think she has self-diagnosed with Asperger's syndrome, and I seem to recall that she has a history of schizophrenia in the family or something like that. But you know, ZMax is a tool for people to just take a look at the sleep structure. It's not really a clinical tool to determine if you have any neurological abnormalities. For that, you really need to go to a sleep clinic and, you know, put on at least 16 electrodes and for trained sleep technicians to figure it all out. I mean, you need people that have looked not only at signals from healthy brains, but signals from brains with all types of conditions, taking all types of medications. There are some medications that you take and they will alter your sleep EEG. So all these lessons are supposed to do is allow a healthy subject to figure out what their main sleep cycles are and score their own sleep. I think she's a healthy subject. Just looking at the EEG is a little bit scary because there's so much zigzag in all frequencies. But hey, it happens. We're not all the same. That's why a lot of these gadgets that you get on the market that say that they're gonna, you know, score your sleep and they output a beautiful hypnogram. Yeah, but is the hypnogram correct? Is the big question. You're seeing how much variability there is. It's even hard for a human who has human level vision to go in and figure out what's going on. And as I've explained, even if you go on PubMed and where scientists are posting research articles about the cutting edge ways of automatically scoring sleep, it's like they're not even accounting for the phenotype differences. So yeah, it's bad. That's why, you know, all over the world in sleep clinics, doctors and researchers, they don't use algorithms. They get somebody who does only this. Their job is just to score sleep. That's all they do all day, and they do it. And so it's still a manual process because there's so much variability. And between phenotypes and also with all the artifacts, like, you know, I told you here that the person is moving, and like in regular polysomnography, they don't really have accelerometers. So like the sleep technician might only be seeing the blue signal. So it takes a whole other, you know, degree of expertise to not know that this was movement and to figure out what was going on. I mean, if it's that extreme, they probably know that the person was moving around, but many other times, like, I don't even know what this is, this sudden spike. I know the person is awake at this point because I'm seeing all this mess, but if they weren't awake and I saw this, I would say, I don't know, malfunction or something. They're probably hitting the device in some way, although they're not moving, because I'm seeing the noise has that spike as well. Look, I have no idea, but it doesn't really matter. All that matters is you can locate the sleep spindles, you know when the sleep cycles are, and already by doing that, even without looking at the signal in detail, just using the spectrogram, you can already look at your own sleep and figure out your sleep cycles and sleep stages. And that's all interesting stuff. I hope this has been interesting. I hope I haven't made it too hard. I will probably organize the material a little bit better for the upcoming lessons, but I just wanted to give you an overview of different people, different types of brain activity, and explain some of the things that might vary between one person and the other. Otherwise, if I had just left it at the first video and passed and moved on beyond the spectrogram, it would be a little bit misleading, because you would be looking perhaps at some point at your own brain activity and expect to see exactly the same type of activity that we saw in the first video, and it might differ. It might differ a lot. But, you know, there is some regularity, so it's totally doable, especially in the sleep spindles, which is the key characteristic here that shows you where your slow wave sleep stages are. And everybody has these. There's only one person that I've found so far that does not have the sleep spindles. And it's so rare that, like I told some researchers, we actually went there together with the person that I had obtained the EEG from, and I told them, this person does not have sleep spindles. And they're like, no, it's impossible. Your machine is broken. I was like, no. And then we actually did a PSG session with him in the sleep lab with ZMax and gold standard PSG. And then he was forced to admit, yeah, that's true. Your friend does not have sleep spindles. And the friend is still worried about it, but he seems to be functional anyway, even without sleep spindles. I don't know how he does it. You will probably most likely have sleep spindles, and you'll be able to see them, and they're going to look just about like the ones you're seeing on the screen right now. Thank you very much for watching, and we'll see you soon.